Okay, higher order differential equations. So up to now, yeah, Zachary after class, okay. Up to now, you've been solving differential equations, but usually they're first order differential equations. You know, dy dt equals something, dy dx equals something. So what if we had a higher order differential equation? What if we had a differential equation where we had a second derivative or a third derivative or a fourth derivative in it? Okay, I mean, for instance, if you want to model the movement of a mass spring system, to model that, that's where you have a mass connected to a spring, and the mass is released, well, let's just say it's released and it bounces up and down, and we want to model the motion of the mass with a differential equation. Well, that would require a second order differential equation. So we need to learn about how to solve some higher order simple harmonic motion. That's right, Michael. That's right. Very good. And we need to learn how to solve some higher order differential equations. And in fact, if you have a higher order linear differential equation, and you know how to tell if a differential equation is a linear differential equation of some order. If we have a linear differential equation, we can get explicit solutions for the y variable. So all right. So in chapter 4 here, let me see. I have it in front of me also. I'm going to just sort of selectively pick things, but let's see here. Yeah, our primary goal, because our primary goal in this chapter is to find general solutions of linear higher order differential equations, we first need to examine some basic theory of linear equations. And, of course, this is an old friend, right? This definition here. You're solving a linear differential equation of nth order subject to an initial value. Now, of course, the higher the order the differential equation is, the more initial values you need in order to uniquely solve the differential equation. Okay, and so that is something that you've seen before. That is something you've seen before. And let me just go down here. So, of course, okay. So let me just see here. Okay, so I don't want to get too caught up in the theory, if you don't mind. I want to just kind of, hit on the highlights that you'll need. But sometimes in differential equations, you're presented with a differential equation that is not an initial value problem, but another type of problem called a boundary value problem, a BVP. Okay. So I'm just looking here in the book. So, like, for instance, in section 5.2 in the book, they talk about boundary value problems where they model deflection in a beam. And deflection in a beam can be modeled with a boundary value problem. So here you have a differential equation subject to two conditions, but notice the y sub a equals y sub 0 and y sub b equals y sub 1. For initial value problem, you would have to have a restriction on the solution, but also on the derivative. Okay, but here you you don't have a restriction on the derivative y prime. You have a restriction. You have two restrictions on the solution, and so that's called that's called an initial value problem. I'm sorry, a boundary value problem. Okay, and so if we look at an example here, okay, where you have x equals c1 cosine of 4t plus c2 sine of 4t, okay, that is a two-parameter solution to the second order differential equation, x double prime plus 16x equals 0. Okay, so that's something that you've seen before. But what we want to do, let's suppose that we want to put two boundary conditions on our solution. X of 0 equals 0 and x of pi over 2 equals 0. Well, if you do that, the boundary value problem will actually have many solutions. And you've dealt with problems like that where you have restrictions on the solution, and you have like infinite number of solutions. You don't see it much, but you have seen it. And they're saying here that if we were to work this problem out, if we were to, put in the initial conditions, then the family of solutions for this problem would be x equals c2 times the sine of 4t. So it's very easy to do. You've done this kind of thing before, putting in conditions and into the solution and solving for the parameters. And so what they're doing here, is they're showing then that, hey, look how many solution curves exist for this boundary value problem. All you're requiring is that at when t is 0, x equals 0, so the solution has to pass through the origin there in the picture in figure 4.1.2. And then you're requiring when t equals pi over 2, x equals 0 also. So there in that picture in figure 4.1.2, the solutions are passing, all those solutions for different values of c meet the boundary value conditions. Okay, so a boundary value problem can have multiple solutions. It can have many, it can have no solutions, it can have one solution, or it can have many solutions. Okay, and so it's something that you should be aware of. And they come up prominently in the textbook again in section 5.2. That's where they study applications of boundary value problems. And for instance, the deflection on a beam between resting on two, I don't know what you call, like a bridge, resting the two ends there, where the bridge connects at the two ends. Those are your boundary values, and there are other conditions too. But so that's a application of boundary value problems. But we are, I mean, those are nice. It's good to know. But we are, our attention is certainly on initial value problems also. And so we have to, get comfortable with a little bit of terminology here. So this differential equation is said to be homogeneous. Okay, why do you think that is? Why do you think that is? Oh, and by the way, let me see if I can highlight the diffie-q below. I guess this differential equation is, okay, non-homogeneous. All right, so, well, what's the difference between these two linear differential equations in 6 and 7? What's the difference between them? Very good, Ann. That's exactly right. The first differential equation has a 0 on the right-hand side. The second differential equation has a function of x on the right-hand side. Yes, question, Thomas.
No. I was going to mention that the other one is equal to a specific function. But that's the difference.
You're exactly right. Exactly right. And you know, they give a little, two little examples here in the text. You know, the here 2y double prime plus 3y prime minus 5y equals 0 is a homogeneous second order linear differential equation, whereas x cubed y triple prime plus 6y prime plus 10y equals e to the x is a non-homogeneous uh, 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 linear differential equation. So, all right, this is nice. This is nice. Let's continue on with this. Let's continue on, and you know, sort of get to the get to where we need to go here. Okay, there's something called a superposition principle. Okay, superposition principle. Okay, if you have two or more solutions, if you have the sum of two or more solutions to a differential equation, to a homogeneous differential equation, that the sum of those solutions, as they show here, is also going to be a solution to the differential equation. Okay, take a look at the theorem. Okay. And so basically a linear combination of solutions to a homogeneous differential equation is itself a solution to that homogeneous differential equation. It's called a superposition principle. Okay, so the question is, well, all right, how are we going to find then the y1, the y2, the up to yk of x? How are we going to find all the little possible solutions? And we will be getting to that. We will be getting to that. But this is the superposition principle, and it's not hard to prove, by the way. It's not hard to prove. All right, and it's gonna be intuitive to you pretty soon as well. Okay, let's continue on here. Let's continue on. Okay, so okay, example 4. Example 4. Okay, so suppose we have these two functions and they're both solutions of this homogeneous equation. So y1 equals x squared and y2 equals, I wonder if they have a, oh yeah, x squared times the log of x. Okay, so they're telling you, hey, these are two solutions to this homogeneous linear differential equation on the interval 0 to infinity. By the superposition principle then, the linear combination of those two solutions is also a solution of the differential equation. Okay, it's also a solution. Okay, so if I, let me just remove the highlight here. So here's the, and incidentally, well, that is a solution to the differential equation as well. So you really have three solutions here. You have y1 equals x squared, you have y2 equals x squared log of x, and then you have a more general solution, which is a linear combination of the two homogeneous solutions. Okay. Okay, now something too, you'll notice that these two homogeneous solutions are independent of each other. So like y1, and what does that mean? Well, all right, y1 equals x squared and y2 equals x squared log of x. Are they constant multiples of each other? Are these two, I wonder if, you know, well, hold on, yeah, okay, hold on, let me highlight it. I want to try to highlight it if I can, but it kind of wants to make it big, I guess. Let me see if I can get it. All right, well, you see them there. Okay, so y1 equals x, y2 equals x squared log of x. Are these two solutions multiples of each other, constant multiples of each other? Can I take a constant times y1 and get y2? Yeah, I know. I'm doing the best I can here. Hold on. I'll tell you what, let me just deactivate. Hold on. I can see y1, but it's a little, oh no, you're right. Okay, so I'll just have to leave it like this. So y1 equals x squared in example 4. y1 equals x squared and y2 equals x squared times the log of x. Are they, excellent, are they constant multiples of each other? And Matthew says no. Let's see, Thomas says if you double click on the screen, it will zoom in on the screen. All right, hang on. One moment. Gosh darn it, this thing. Hold on, class. I got to get to the screen first. Oh, man. All right, Thomas. Thank you. Thank you. All right. So, yeah, y1 equals x squared, y2 equals x squared log of x are not related to each other. They are totally different functions. They're independent of each other. And it turns out that, you see, what we ultimately want to do is we want to find a general solution to the differential equation, a very general solution that incorporates all possible solutions. And so what we're going to learn, what you're going to learn is that if you can find all the independent homogeneous solutions, the linear combination of them will be a general solution. Okay, and all right, so let's see here. Let's continue on. So this idea of linear dependence and independence, it's something that comes up in Math 284 in linear algebra, but it comes up here as well in the course. So a set of functions is said to be linearly dependent if there exists constants, not all zero, such that if you take a linear combination of the functions, you'll get it equal to zero. Okay, in other words, the functions are related to each other by that equation in definition 4.1.1. Okay, they're related to each other. Now, to see this, it's really best to look at an example. So let me go to an example here. I like to go to the examples because I just feel good going to the examples. Okay. All right, one moment here. All right, so here you have a set of functions. In example 5, f of 1 equals cosine squared of x, f of 2 equals sine squared of x, and f sub 3 equals secant squared of x, and f sub 4, that function is tangent squared of x. Well, that set of functions is going to be linearly dependent on the interval from negative pi over 2 to pi over 2, because we can find a linear combination of those functions that will equal 0. Namely when C1 equals C2 equals 1, and C3 equals -1, and C4 equals 1. Okay, and that's based off of these trig identities. Based off of the trig identities. You see that? So these functions are connected to each other. It's like they're related. They're related to each other by that equation where C1 equals 1, C2 equals 1, C3 equals -1, and C4 equals 1. And so those are linearly a linearly dependent set of functions. Okay. Okay, are there any questions on that? Well, and I understand what you mean, what you're saying. Here's another way. You can think of it like this. You see below here in the mind tap, they're saying that this might be a nicer way to think about it. A set of functions is linearly dependent if at least one of the functions can be expressed as a linear combination of the remaining functions. Okay, if one function can be written in terms of the other functions, couldn't we say there's a dependency between the functions?
Yeah, of course.
Yes, and that's right. And so that's right. So all right, Ann's comfortable with that. But now Matthew says tangent sine over cosine, but the dependence relationship has to meet. Thank you, Thomas. A dependence relationship has to meet this condition here. This condition here is the one in order. So just because tangent sine over cosine doesn't mean that we're not really. We have to find constant C1, C2 up to Cn that where this definition is satisfied. Here's another example. And I'm doing a few examples because in your section 4.1 homework, and I know you're going to be worrying about the exam, but the 4.1 homework that'll be due next week, that there are problems where, like multiple choice, are these functions linearly independent? Yes or no? And so you got to be careful when you answer those questions, right? Because you have one chance to get them right. All right, so here's a set of functions in example 6. Okay, here's a set of functions. Hold on, let me get that thing off. Okay, I see 4 functions here, and they're linearly independent because you can take the second function. And write it as a linear combination of the first, third, and fourth functions. So those functions are linearly dependent in example 6. So some of the problems that you'll see, you can just, you have to, now, of course, class, of course, you have to think about it a little bit. They just didn't come up with 1, 5, and 0 right away. But it's like a little puzzle, but it isn't too hard to see. If the functions are linearly dependent, it's not too hard to find the constants. So it takes a little time, but all right. Are there any questions so far?
Professor, so what they're saying is that the domain is what they can share. That's the way that they are.
Well, over the interval 0 to infinity, and that's because you got the square root of x there.
Yes.
Those functions are linearly dependent. All it means is one function can be written as a linear combination of the other functions. That's what it means.
Any of those?
Any one function can be written as a linear combination of the other functions. They just chose to write f of 2
Uh-huh.
as a linear combination of the other three functions. But I could have written f of 3 as a linear combination of the other three functions.
Which is F2 minus F1 minus F4.
Right. Yeah, I'd have to write it down actually, but you know, I'll. But you got the right idea. You got the right idea, Thomas.
Thank you. Okay.
All right. So okay. So clearly establishing. I mean, what we're interested in. I mean, well, we need to know when functions are linearly dependent and when they're linearly independent. And you know, what if you had functions, you know, what if you, I mean, here we have 4 little functions, but what if you had 10 functions? Okay, what if you had 10 functions or 20 functions, and you wanted to see if those functions are linearly independent or dependent? How would you go about that? Well, there's a determinant called a Wronskian in definition 4.1.2. Okay, this is called a Wronskian. So, how many have maybe seen a Wronskian in another class? I'm not sure if you have, but it's a determinant. Okay, those bars, those vertical bars mean determinant. So, like for instance, if let me just go to the whiteboard here. If I were to take like 3, hold on here. Let me take 1, 2, and 3 and 6. Yeah, well, good, Michael. Now you're gonna see. Now you're gonna see. So this here is a determinant, and the way for a 2 by 2 determinant, the way you compute a 2 by 2 is to do the cross, like the well, let me just show you here. This is going to equal 1 times 6 minus 3 times 2. Okay. How many have computed a determinant for a 2 by 2 before? Okay, Anne has. And it comes up, of course, in linear algebra a lot. Christopher has, Thomas, Matthew, sure. Now, incidentally, what's this determinant? Yes, you did, Matthew. Linear algebra, that's right. Oh, okay, good, Christopher. It equals 0. Kind of interesting, right? The determinant equals 0. What do we notice? What do we notice about the columns here? The 1, 3 column and the 2, 6 column. We could call them vectors. What's interesting about 1, 3, and 2, 6?
They are the same. The products are the same.
Yeah, they're linearly dependent, and also if you go 2 times the vector 1, 3, that's right. When you have a determinant of 0, the columns of the determinant are linearly dependent. And notice that 2 times the vector 1, 3 is equal to 2, 6. Okay, so, I mean, very interesting, right? So the fact that one vector is a multiple of the other vector means the two vectors are linearly dependent. Now, what about functions? Could there be an analogous situation for functions, to determine if functions are linearly independent or dependent? Well, there actually is. There actually is. Would you agree that a function and its first derivative characterize a function in a sense uniquely? I mean, think about like finding the flavor of a function. Flavor of a function. That's how I like to think of it. We have all these different functions. They act in all these different ways. But certainly, if I wanted to learn about a function, I would look at the function, but then I could learn more by looking at its first derivative, right? Hence calculus. Well, all right, let's say I had a second function. And in that column, in the second column, I'll have the second function along with its derivative. And suppose that the determinant, of this, which would be, of course, f1 times f2 prime minus f1 prime times f2. Okay, hold on here. Let me get my little eraser out here. Okay, suppose that were equal to 0. Okay, I never thought about the product rule, but it's interesting, Michael. I never even thought about that. But let me ask you, if that were equal to 0, what do you think that would imply about these two functions? Well, they're linearly dependent. They're linearly dependent. Linearly dependent. Okay. Linearly dependent. I mean, I guess what I'm trying to do is, this here stands for the Wronskian of two functions. And you'll learn that if the Wronskian equals 0, then the functions, let me write that a little better, then the functions are going to be linearly dependent. Yeah, Michael, and the thing is, the way I think of it, so I see this and I say, well, why is that true? Why is that true? Well, I think about this little example here, where I take two vectors that are linearly independent. Their determinant equals 0. Why would it not also apply for two functions? Why should it not also apply for two functions when you have the column vectors in the determinant being the function and its determinant? I mean, why wouldn't that be true? I guess what I'm trying to give you an intuitive feel for this. So I'm going from something that is very intuitive to something that, okay, well, I can make the jump that if the Wronskian is equal to 0, then the functions are linearly dependent. And, you know, okay, the columns in the determinant are the function and its derivative for two functions, because, you know, that the function and its derivative characterizes the function, just like vectors are characterized up here. And if the Wronskian is not 0, that's right, Michael. If the Wronskian is not equal to 0, then the functions are linearly independent. That's right. That's exactly right. So on that note, let me go back to the ebook here. Okay, now you'll notice, and I think this is as big as whoops, hold on. If you have more than 3 functions, like if you were to have 3 functions, the columns of the Wronskian would consist of the function, its first derivative, and its second derivative. So if you're going to see if 3 functions are linearly independent, you need to learn about the function and its first 2 derivatives. Does this help a little bit, that example I did on the whiteboard? Does that kind of help you intuitively appreciate? Okay, Ann likes it. Good, good. I like it too. I like it too. Thank you, Thomas. I like it too. All right, well, on that note, thank you, Michael. On that note, let's continue on here. So, of course, all right, let's continue on. So, criterion for linearly independent solutions, theorem 4.1.3. Hold on, did my book disappear on me here? Hold on, let me get it back. One moment, class. I don't know what happened there. Yeah, I see that. I see that. Yeah, it does that. I don't know why it does that. I don't know if it's a safety feature or what. I don't know. But okay, one moment here. Okay, so now, yeah, if your Wronskian is not equal to 0, then your solutions to a differential equation would be linearly independent. Okay, and so what you have to do, like for instance, if we continue on here, hold on. Hold on. No, I don't want to go that far. Wait, not yet. Yeah, so here, man, hold on. Yeah, so here they say, okay, suppose we have these 2 functions. Suppose we have these 2 functions. They turn out to be a solution to this differential equation below. Are those 2 solutions linearly independent or linearly dependent? Okay, well, intuitively, you might think they're linearly independent. Let's see. One moment. Hey, Alan, I'm actually teaching now. Can I call you back later? I'll call you back in the morning. All right, thanks, Bart. Okay, so let me see. I heard a chat thing there. Hold on. Oh, yeah, that's right. I know. All right, so thank you, Justin. I appreciate that. Okay, so, you know, the announcement I'm going to talk about in a few minutes, I'm going to email to everybody. Okay, I'm going to email to everybody. So you compute the Wronskian, And in this case, you get actually a constant. It has to do with the trig functions. So this is part of it. Now, if you do have linearly independent solutions, okay, you're going to have what's called a fundamental set of solutions. If you have homogeneous hold on, if you have homogeneous solutions to a differential equation, then and they're linearly independent, then you have what's called a fundamental set of solutions. And why is this important? Well, let me show you why that's important. Now, one moment here. I mean, I know why it's important, but I'm trying to get to the right theorem. It's theorem 4.1.16. So let me get to that theorem, and then we'll stop there. So first of all, well, actually, no, theorem 4.1.5, that's the one. What's the general solution to a homogeneous differential equation? Okay, what's a general solution? Well, it turns out that if you have a fundamental set of solutions, y1, y2 up to yn, to the differential equation, and the fundamental set of solutions means that the solutions are all linearly independent, then a linear combination of those solutions will be the general solution to the differential equation. The general solution. You don't need to look elsewhere. That it will be the general solution. All right, and that's really some key ideas behind section 4.1. Are there any questions? Okay, I'll stop the recording.